cross-validation, data drift, principal component analysis. The landscape of modern data science often appears as a chaotic swarm of disconnected terminology. Teaching these concepts as an unorganized stack of individual algorithms leads to fragile, poorly architected systems that lack a cohesive internal logic. Disparate techniques can be unified under a single taxonomic framework, a data science periodic table. By constructing this matrix from first principles, we can map the specific interactions between every mathematical element in the stack. We will use this framework to trace the path as raw data is mathematically refined into validated insights. Mapping algorithms to a grid defines data science as a sequence of engineering dependencies rather than a collection of isolated math problems. The y-axis of the matrix tracks data maturity, moving chronologically downward from raw data sources to the final delivery of insights. The x-axis represents the analytical activity, progressing from left to right through acquisition, processing, and evaluation. The first row of the matrix handles raw data. This starts with ET, for extract, transform, and load, moving raw data from original sources into a centralized system. We then move to D, or data ingest, utilizing atomic streaming to process incoming data. The second row represents prepared data, where we introduce the element E, for encoding. Encoding converts categories, text, and dates into the numerical vectors required for downstream computation. We then apply CD, or data cleansing, to finalize the preparation stage. An architectural gap in these foundational ingestion cells results in corrupted data that compromises every subsequent modeling layer. The third row focuses on refined data. We begin with RE, or regression, to estimate the mathematical relationships between our variables. Regression provides the mathematical parameters required to generate SY, or synthetic data. Synthetic data is deployed by architects when organic datasets are too sparse or restricted for effective training. At the far end of the refinement row, we place BO for bootstrapping. Bootstrapping creates resampled datasets to establish confidence intervals and estimate the variability of the data. This row is significant because it dictates the statistical confidence limits for any future predictive capabilities. The model data row begins with ST for structured data, which organizes information into schemas and graphs for easier use. For high-dimensional sets, we rely on PC, or principal component analysis. PCA compresses dimensionality by identifying and maintaining the highest possible variance within the data. We then use CL, or clustering, as an unsupervised method to find natural patterns and groupings within not compressed data. To increase accuracy, we implement S, or ensemble architectures. Ensemble systems allow different model types to vote on a particular outcome, reducing the bias of any single algorithm. This row concludes with C for simulation and G for distribution generation to map out hypothetical outcomes. A model's output is a direct reflection of the dimensional structures established during the refinement stage. The far right column, Group 5, handles evaluation, creating a continuous feedback loop. MET, or metrics, quantifies baseline performance. Below that, VA, for cross-validation, rotates training and testing data slices to check model robustness. We monitor system decay using X for explainability, which decodes feature importance to ensure the model's logic remains sound. Drift, or drift, is the specific diagnostic tool used to monitor how model performance shifts as real-world data changes over time. Finally, BA, or Bayesian models, incorporate prior knowledge distributions to manage uncertainty in predictions. Without this dedicated evaluation column, a data architecture cannot detect when its own predictive logic has begun to degrade. Moving into the realm of quantum mechanics introduces a new set of elements, yet the underlying taxonomic logic remains constant. The validity of this framework depends on its ability to categorize data operations, even when the hardware environment changes entirely. If we map the quantum lifecycle directly parallel to the classical one, we see an identical structural flow. QA, or quantum accessible memory, is the structural equivalent of ETL, moving data into quantum circuits. QE, for quantum encoding, mirrors the classical encoding step by translating data into amplitude or angle qubits. The sequence continues through QO for quantum modeling and QN for quantum evaluation metrics. The functional requirement to move, encode, model, and evaluate data persists, even when the underlying hardware environment changes. Returning to the classical table, we reach the final row, validated insights. The terminal element of the entire periodic table is Go for data governance. All upstream mathematical operations are ineffective without governance rules to ensure data quality, security, and compliance. This table allows architects to audit software vendor pitches by identifying missing pipeline dependencies. It also provides a visual diagnostic to reverse engineer and troubleshoot failing machine learning models. Data science is a sequential engineering pipeline where a final insight is the product of its prerequisite stages.